All right, so here's class 16. I'm going to do this in two parts. I'll do the first example, the one that I covered in class. I'll try to quickly go through and discuss the Excel, SolidWorks, and MATLAB approaches in that order, and to make a comparison between them. So here's the problem. We previously did the position analysis for a full rotation in earlier examples and videos. I believe that you can look those up. I think class 15 is where I have done this problem for full rotation. But I've adapted it somewhat. Now I've gone and used theta 2 is equal to 75 instead of 40. I've also made the length here of the coupler 150 and changed the angle to 15. And I want to find the velocity at point P when it's at this position. And then second, I want to find it for a full rotation in Excel, MATLAB, and SolidWorks, not necessarily in that order. And then, all importantly, I want to compare. When I get to the MATLAB part, if you don't have to do the MATLAB, you probably can skip over that and go towards the end of the video. In the position analysis, I could use my tools that I've previously created, and for 75 degrees, I can find that theta 3 is 18.25 and theta 4 is 72.3. The velocity analysis, spelled wrong, at 75 degrees, I can get at omega 2 equal 25 degrees, I can get the omega 3 and omega 4. I'm only really going to need omega 3. The position that I chose, I thought it was pretty good, but still that's kind of a small value right there. Now I want to find the velocity of P, and in order to do that I need the velocity of A, because I'm going to use the velocity of P is going to be equal to the velocity of A plus the velocity of P with respect to A. So I go through and I find the velocity of A by taking the magnitude omega 2 times J E raised to the J omega 2, not omega 2 but theta 2, and put all these together, and I'm able to find this. So I need this. I've also included these down here, even though I think I might have gotten these backwards, by the way. But pay no attention to that. But anyway, I did find what a VB and VB with respect to A is, but I don't need that. What I really need is VP with respect to A. And I can find that the same way that I've been finding other velocities after I've got the omegas, is I could take the AP right here, this distance, times omega 3. Now, why omega 3? Because this link right here, that's a solid link. That's all one part. It all rotates at omega 3. And then J, E to the J, and the angle here now is going to be theta 3 plus theta plus delta. So it's theta 3 plus del, and so we'll write that in here, theta 3 plus del. And so that from position analysis is 18.25, and we know this is 15. It ends up being 33.25 degrees. So we plug in all the things we know. We know that AP is equal to 150. Omega 3 was 0.4842. I replaced the J and the E raised to the J stuff by the Euler identity. Actually, Euler identity times J, and that's 33.25 inside the sine plus a J of the cosine of 33.25, and then I end up equaling negative 39.82 plus J, and we have 60.74. These are millimeters per second. And if I want VP now, VA plus VP with respect to A, I take my A that I got, negative 965.9, and I add to it my negative 39.82, and then I add the J parts, 258.8 plus 60.74, and you can see that the relative, doesn't actually isn't all that large. But we're just doing this as a means of comparison. And I get a negative 1006 plus J of 319.5 millimeters per second. So that's the thing by hand that I want to compare in my other methods. So I'm going to keep all of this because I want to be able to compare it, and I got to flip my screen over. I don't know what that looks like in the video. Okay, and now I can, let's see, I'll go to Excel. And I'm going to delete this guy right here. So what I want to do is I want to start with something that you've seen before. Okay, yeah, so this is, I think, the results that we got from the last video, where we made for a full 360 rotation, where we have a generic, where I did the example, but I kept it over here. I think I did modify this for things that are similar to your homework, and maybe I should have waited, but this is where I'm going to start from. So I'm going to make a copy of this as we go through the thing. And so I create a copy, and I'll put it like right here and get rid of it later. So the things that I modified from this example was that now AP is equal to 150. We're taking a look at 75. This actually isn't necessary, but it's going to change what the position looks like. And then this was going to be 15, and then omega 2 was 25. So we take a look, and sure enough, this is what the assignment. Of course, I've used this to show you what this looks like, but we'll confirm this later on that's going to be what the coupler curve looks like. We'll do that in a couple different ways. We also we'll look later. We'll find that the velocity down here. This is actually for like 4 rotations or something along those lines. So I actually want to get rid of some of the things here. So while I'm here, let me just get rid of everything that's going to be above 1080, right? So I'll just delete that. But what I care about, okay, so the very first things first, probably should have gone here first. I need to take a look at 75. What it looks at 75 degrees of theta 2. What do I get for the velocities? And you can see I get negative 1004 and 318.4. So I could bring those over to here, and maybe I'll just go ahead and paste those as a picture here, and we could put those right up there, and we could see that those are darn close. If I instead try and change my increment, let's take it to 2.5 degrees. All right, so now we have to scroll down, and we'll find we get an answer of negative 1005.3 and 319.3. So you can see that we're getting actually closer to what we found before, what we found by hand. And then we could go even better if we wanted to, maybe 1.25 maybe. You were only asked to do it for 5 degrees, but I do think it's worth taking a peek and seeing what the effect of this increment is going to be. And if we do that, we get, as far as we know, that this is almost exactly the right answer because of the sig figs that I used as part of this. You can see that 1.25 as an angular increment was pretty darn good. So let's go back up here, and we don't need to. I want to go for the full cycle rotation now, right? So that was the answer right there. But let's go back, and we'll make this increments of 5 again, and we'll see what happens when we do our SolidWorks and make a comparison there. All right, so in SolidWorks, and I'll open this up right here. I have made the piece and made the assembly right here, and I also, to start off with, made the crank in line with the ground right here with a coincident thing. Well, I'm going to, when I go to make a motion study, I'm going to go ahead and remove that coincident thing. So I'm going to suppress this coincident mate. Right. So let me go scroll back up here. One thing I'm going to do is I'm going to disable this the creation of those keys, because I hate that. We're going to take that, instead of animation, we're going to have motion analysis, right? And we want to apply a motor to this crank. It's going the correct direction, but we're in RPM, and we want to be in radians per second. So let's calculate that. So I'm going to go back over here, and I'll write all this stuff down in here. So I'll write my calculations. That 25 radians per second. We could divide that by 2 pi radians per revolution, and that's going to bring revolutions back up at the top, and multiply by 60 seconds per minute, and then we're going to get 238.7 RPM. So that's what we will place onto our thing here. 238.7, and boom. We only want 3 rotations, so we want to figure out how much time 3 rotations is going to take. So what did I do down here? I said 3 revs divided by, and I could have done this in a couple different ways, but I took that 25 radians per second divided by 2 pi. Once again, that's radians per revs right here. And okay, so that's actually if I just divide that right there, right, the 3 revs by that right there, I get that it's going to be 0.754 seconds. So that's going to be tough to do in what I have down here, but I can do it. What I have to do, or I can get close at least, I'm going to move this tile over. Now I need to zoom in to be able to see that better. And okay, I went too far. So there's 7.75. I can actually get closer. Let me see. Bring this over. Where'd you go? Okay, I could go closer to my. Let's see. How close can I get? Let's see. Let's try it. All right, there. So here is 7.75. What increments will it let me get? Where does this guy right here? This is 0.755 right here. Here's 0.75. Okay, so I'm gonna get really, really close, I think. 0.7535. So here is 0.754. Okay, great. And if I were to go ahead and hit solve right now, let's see, looking at this thing, I'm gonna, let me go ahead and solve it. And if let's see, playing the thing back. That almost lands exact. That's almost exact. Yeah. All right. So let me take a look at the results first. And I hit this graph button right here, and I want to hit the displacement and trace path, and I'll pick the point that's right up here, that vertex, and you can see how bad that is. We could also take a look at the velocity right here. So we once again, we'll go the displacement, velocity, acceleration. We go linear velocity. We'll pick that point again, that vertex, boom. And we want to create a new plot, and I think we're going to get, is it going to do it for me? Here, I said okay, okay. What's wrong with you? How come you're not? Oh, I need this. I'm sorry. Okay. I need the X component. Let's go with the X component right in there. All right. Boom. You can see how bad that is. Let's also take a look while we're here, and let's take a look. I think this will work. I've had a little bit of a problem with it, but let's see. Linear velocity in the Y direction. It doesn't want to do it. Come on. There you go. And we want to add this to the existing plot. And I don't know why it does this. It gives me the wrong units the first time I do this thing. So I got to like figure that out at some point. This velocity here. I'm going to edit this. And it's looking through the thing. You get the Y component and linear velocity. I don't know why it does this. Let's see, do it again. Yep, okay, now it works. I don't understand what that quirk is, but you could see the range. It was like 0.2 down here. Now it's into the correct range. And by the way, if you want to change these to the correct to something that's going to work, you can right-click, go to here. I think the default in many of in one of the other programs was 1500 and 3000. That was a pretty decent range. And then this one was like increments of 500, and minor was 100. We end up with a sensible scale right here. And I'm doing this so that I could make these match to each other as we're looking at them. Otherwise, as soon as you see the next graph, you're going to think that the thing changed like crazy. So let's make them something consistent with each other because they're plotted on top of each other. That's my purpose here, to explain this somewhat unnecessary process right here. All right, so now you see that these are the same scale on the left, so that we're comparing. Now, this is not enough increments, and if we want to know why, we can go to this little gear, and we can see that there's only 25 frames per second, and we don't even have a second here. We only have 0.754 of a second. So what we want to do is figure out how many frames we need to be equal to the same thing that we were using before. All right, so and there's unfortunately not going to have exact right amount. It's because of the radians per second kind of thing, and the fact that this ends up being a non-even number. We probably should have chosen a standard RPM, and that would have been able, and we could have like figured out what, because we can only break down the thing by whole number steps in the solution of the thing in SolidWorks. So maybe we should have anticipated that and made the other ones match the time scale for this. But that's what we're kind of left with. So let's just go ahead and proceed anyway. 3 revolutions. So all right, 3 revs times, let's say we could go 5 degrees. 5 degrees by 360, no, let me go the other way around. It's going to be 360 degrees divided by 5, which ends up being 72. So we're left with this 216. That's going to be the number of steps that we have for 3 revolutions. If we take those 216 and divide them by 0.754, we're left with 286.5 steps per second, right? So we had a choice. We could either go 286, this should be a point decimal place, or 287 when we come back up to here. And so I think I decided to go 287. Okay. That's the best I'm going to be able to do to divide up the time that we have right here. I could probably have worked it out the other way and just messed with the amount of time, because it doesn't really need to be 3 rotations here. We just want to get the same time step. But I didn't work it out. So maybe you want to do that. You want to work out what time step do I need to have so that my results will be exactly the same time steps as this. Because that's going to give me a source of error. But let's go ahead and solve it now with that time step. I'll hit the recalculate button here, and we'll watch, and we'll see, wow, that's much smoother path right there. And when we get to the end right here, almost there, kaboom. All right, so now you can see how much smoother we are. And if we want to export this now, export this to Excel, we right-click on this down here and we export to a spreadsheet. We don't really care about this. We care about these. So we go over to the sheet right here and grab all of those and hit our Control C and come back over to our Excel. And we can, I believe right here is the correct cell we want to go to. Is that true? And by the way, I can't see those numbers, so I'm going to go auto column width. Okay, so now I can see them. And all of these things, well, this right here, these are both the VX and this right here, but this one is for SolidWorks. So we want to try to remind ourselves right here, and I'll merge those cells above here so we know that that is the SolidWorks comparison. Now, if we plot this, if we were to plot these on top of this right here, they're really going to be close to each other. It's going to be difficult to say. So when we go to look at them, and once again, I really wish I had the same time step. You can see what the difference in the time steps are going to be. I could just subtract one from the other, and you'd be able to see that they are not identical time steps. I mean, right there, they're going to be 0, but let's put them into scientific notation here so that you can see how far they go down. Right there it's 0, but let's see, that's going to have to, you can see that it's pretty small, but it's getting bigger because the time step, well, not bigger, but it's actually getting smaller because the time step here is smaller than the one that's over to the left. So what we could have done is, if we wanted to, we could come back to this and we could have solved this again for 287. Or, excuse me, that's the wrong one. It's the next problem. We could solve this one for in the motion study. We could. It's going to be a little shorter than it needs to be. Whoops! I didn't mean to resolve this, but I'll let it do it all the way through. Oh, I see. Okay, wait. It's stuck because it's the wrong one. Okay, this is the one. This is the one that we did, and I meant to turn this to. Whoa! What happened here? Did I do this in the wrong one? I don't think so. What's going on? Yeah, I think I need to escape out of this. I need to escape out, right? I think I'm stuck in the middle of it. All right, so is it going to let me do it this time? How come 25 right here? Let's go 3, what did we say, 287? 287. And let's calculate that thing. Ah, that's broken. Okay, so this one is broken. This is the one that I think was supposed to do the thing. Huh. What happened here? I exported this thing. Did this crash or something? What happened? I'm so tired of recording this. This is like my third time doing this. All right. What is going on here? All right, so let me create a new motion study. So I made a little mistake there, so I'm going to cut out this part right here. But let's see, what would happen? I think I prefer to check it out if there was going to be 287 steps instead. So I went back in here and I tried 287 instead and solved for this again. So that's just a little bit difference. So I rounded up that 286.5 that I got and rounded it up. And so now I'm going to get a different spreadsheet here. So I'll export to the spreadsheet again. And it's funny to me that it doesn't show me doing this. It just pops up here behind the thing. So let me grab these instead and take a look at them. All right, so now there's 218 steps, and that's interesting. It's one more than I expected. Okay, so let's see, what does this look like here? And take a look, and it keeps getting the increment down here at the bottom. Interesting. Okay. Well, let me go ahead and switch over to the MATLAB stuff. This was a means of comparing those. Let's just well, no. Let me first do the comparison that I would take of this right here. So if I'm going to compare the SolidWorks, what we're going to compare is going to be the velocity of and the x direction. So let me take this velocity and x direction at P, and I'm going to subtract out the one that I get from SolidWorks, and then I'm going to divide it by the one I got by hand. So I'm just going to, when I say the phrase when I'm talking about the comparison, it's going to be that this one is this percentage of that. And I actually made it in the wrong cell. I'm sorry. So let me, this is the correct place, but is actually referring to that row right there. And so I can take a look at this, and I actually might want to make this a percentage and give it some decimal places right here. And you can see that there's, we're going to end up seeing that there's going to be a periodic difference in right there. Actually, there's a pretty big difference right in there. There's actually a growing difference because, oh, look, it's huge, because it's actually shifting over right there. So we really need maybe to put in some more effort to try to get the correct increments as a means of comparison. But what we can do is to plot them on top of each other as a means of comparison. So that's what we'll do here, is we can add in the SolidWorks part, and we will use, I'll only do it in the X direction. We'll use the SolidWorks time. As long as we're using the SolidWorks time and the SolidWorks X, we can, those two, it's going to be totally valid from there. And then we'll also plot the velocity in the X direction for this right here. So, yeah, I don't see any problem with that. Okay. I think I went all the way down to the bottom of the time. Let's see. Yeah, I went to 233. So let's see this comparison on top of each other, plotted one on top of another. Boy, that's really, really close, huh? We did a pretty good job. Of course, you see that last one. That needs to go away right there. Should probably come in here and format these and take them out. Let's see. Not take them out, but make them smaller lines so that we can really get a look at the thing. So what I would do is for this is maybe like zoom in onto the thing to try to look at it. If working on a project right here, I might want to redo all of this and come through a scheme in which I make the time step be exactly the same, because otherwise I'm not going to be able to compare them. You can see the accumulation of the difference in the time gave me this large percentage. So I'm already gone over the amount of time that I want to make this video. So I think I'm going to make the MATLAB an extension, so a separate video, because I have to clip out some of the stuff, the mistake that I made in the middle. So we'll end this now. But in terms of the instructions, so right there we did it by hand, we did it in Excel, and we did it in SolidWorks.